Just to let you know that the pictures are already on the homepage of the conference, in case you want to see them.
Okay, I think we can start. Welcome to this last session of the conference. The first speaker this morning is Nasser Maklouf from France. He will give us an overview of home type and big home type twisted by algebras and Hopf algebras. Please.
Thank you very much. Good morning, everybody. I am very glad to be here. Thanks to Alessandro and Claudia for the invitation, and I will send my congratulations also to Claudia and thank her for our long collaboration, on which I would like to report today a little bit. I'm going to talk about this twisted by algebra, but of course this word twisted is used everywhere, and in each place it has some meaning. I made the title a little bit more precise. I'm going to talk about this home type and bi-home type algebra and bialgebra. And already Sergei Silvestrov talked about this. I'm going also to repeat some concepts here. And the outline of the talk is this one. First, I will maybe motivate once more why we are dealing with this structure and recall some definition. And then the last part about bi-home algebra and infinities of bi-home algebra. This is mostly the work we did with Claudia Menini, but it's in a quartet, including Florin Panaite and Ning Liu. Let me start. I like to start to introduce this type of algebra by this paradigmatic example. Sergei yesterday told you that it appears first in this Lie algebra of vector fields mainly, and people were interested, physicists mainly, were interested in Q-deforming the structure. What does that mean, Q-deform a structure? It means that you are going to replace the usual partial derivative by sigma derivation or skew derivation. And let me first start with this example. Consider the SL2, Lie algebra, and view it in terms of first-order differential operators, where the generators are here, and you take the usual commutator. And now we want to Q-deform this Lie algebra and replace the usual partial derivative here, delta, by some delta sigma. And sigma here is a linear map, K-linear map, and should satisfy some twisted Leibniz rule. And here the twist appears here where you take sigma of A. Okay, then the example we are going to use is this Jackson Q derivation, which is a quite old Q derivation. In the beginning of the last century it appeared in a different area. And here you take a set of polynomials on T, and this Jackson Q derivation means that you take Pt and transform it in dQpt, defined in this way, pqt minus pt over qt minus t. And this delta sigma satisfies the sigma Leibniz rule, this twisted Leibniz rule, where the twist now here is given by sigma pt equals pqt. In your polynomial, you replace all t's by qt. Now, what about this the sigma on the monomials T to n, and it turns out that the sigma of Tn, this is the Q number n T to n minus 1. Let me recall that the Q number n is equals 1 minus Q to n over 1 minus Q. And now, if we consider the commutator to reconstruct sort of Lie algebra, then here we have to consider also some twisted commutator, as it was mentioned already by Sergei, and we take sigma here, and within this commutator, what you get is that the new bracket with respect to this d sigma of hf is minus 2qf, he is 2e, and ef is 1 over 2, 1 plus q h. And the question now is whether this satisfies Jacobi condition or not. It turns out that it's not. It doesn't satisfy Jacobi condition, but some twisted Jacobi condition, and the modification is here in this term. In order to have a d sigma, you have sigma a d sigma. And this was the motivation for, of course, let me maybe just consider another example before giving the definition. Then you can do the same with Witt algebra. And if you don't like Witt algebra, like physicists, this is centerless Virasoro algebra. And this is the algebra of the derivations of Laurent polynomials. And now, if the generators of this algebra is RT EI equals to T to I plus 1D, and they satisfy Jacobi condition. This is a Lie algebra. But now, if you replace, as we did before, this d by this partial d by d sigma by q. We do a q deformation. Sorry. Maybe this is because of the wine yesterday. I'm so sorry. Then again here you get in the new bracket you get Q numbers, and again here the Jacobi condition is not satisfied by some modified Jacobi condition, where here you can see for the generators EI, EJ, EK appears here numbers which are different in each term. Which means that Jacobi is not satisfied, but what is satisfied, something modified, and what was called by Sergei Silvestrov and his collaborators Hopf algebra, because the structure is modified by a homomorphism. And now let us give the formal definition of Hopf algebra. Then we have the skew symmetry as usual, but the Jacobi condition is changed to Hopf Jacobi condition, where appears here this twist map alpha. Okay, and sometimes we also assume that alpha is an algebra map, and we call this multiplicative Hopf algebra. But to get good results, it's necessary sometimes to use this condition. Now, what is the pending associative algebra for this Hopf algebra? This is what we introduced with Sergei. And now we have to modify also the associator by using, again, this twist map alpha, or the structure map alpha here. And the associator becomes the Hopf associator, defined in this way. And for morphism, it goes similarly. And we need the compatibility between the morphism and of Hopf associative algebra and the structure maps. Now, of course, we can think about the unitality for associative algebra, and the good notion for unitality is not the usual one, but this one, you have to assume that mu x1, this is not x as usual, but alpha of x. Okay? The first test is to check whether the commutator of Hom associative algebra gives a Hom-Lie algebra. This is the case. And the other question is, here we can talk about categories, of course. As I mentioned, we have objects and morphism. And now we have this functor from the category of Hom associative algebra to the category of Hom-Lie algebra. And one can, of course, naturally ask whether what about the adjoint functor. Then we have an adjoint functor, and this was done. The enveloping algebra of Hom-Lie algebra was constructed by Baldoni-Diao using some decorated trees. And you have trees as usual, but you put some decorations, and these decorations in the nodes corresponds to the power of alpha you used. And of course, then the natural question, what about Poincaré-Birkhoff-Witt? For the moment, I'm not sure that we can prove it in general, but in some particular cases, this is possible. For example, it was done by Li Guo, Zhang, and Zhang for involutive Hom-Lie algebra. Some constructions, this one was mentioned already by Sergei yesterday, and this was introduced by Yao. When you can start by a classical algebra, for example, by an associative algebra. If you have an algebra map alpha, then if you compose this alpha with mu, then it gives you a new multiplication, and within the alpha you have a Hom associative algebra. And this way it can work also if you start with the Hom associative algebra, and if you have again an algebra map, then you compose and get a new Hom associative algebra. With Florian Panaiti, we provide also some other construction generalizing this Yao twisting using pseudo-twister, which we generalize to alpha pseudo-twisters. And we got this result, for example. If you have, then we start with an associative algebra again. We consider an algebra endomorphism, and the map T from A tensor A, this is our alpha pseudo-twister, and T1, T2, the companions maps. And if they satisfy, all these maps satisfy this four condition, then the composition mu composed with this T, and the alpha provides a Hom associative algebra. And this indeed generalize this Yao twist, and you can get your Yao twist just by replacing T by alpha tensor alpha. And this is the companions map. Okay, now to get to Hom by algebra, we have to dualize things. And as it was mentioned by Sergei yesterday, then we have to dualize the associativity, and then we get a co-associativity, and again here the co-associator is twisted by some map, some structure map, which we call here beta. And we have co-unitality with some epsilon satisfying this condition. And again here, you can see that we don't have identity, but we have beta instead of the identity. For Hom by algebra, then we have to mix these two structures, Hom associative algebra, Hom co-associative algebra, and assume that delta and epsilon, as usual, are compatible or are algebra maps, which can be written in this way. In this case, again, we can construct a convolution product. Then, if you start with the Hom by algebra, then over the morphism of V, you can construct a new product, a convolution product using mu and delta as usual, and this forms on Hom VV Hom associative algebra, which is again unital, and the unit now is not the identity but alpha composed with F composed with beta. then we can define what Hopf algebra is. Then it's just a bialgebra with an antipode, which is the inverse of the identity with respect to the convolution product I mentioned already. Okay? Some properties. The antipode is unique as usual. You have this the composition. For primitive element, the epsilon of x is 0 as usual. And if we have a primitive element, then epsilon of x is 0. And the commutator is again a primitive element. Then here, maybe what is interesting is that the primitive elements of H form a Homely algebra. One example, yeah, here we have this twist map, or this Yao twist works. If you start with a bialgebra and a bialgebra endomorphism, then you, by composition here, you can get Hom bialgebra. And what I show here is that if you start with this quantum group UQSL2, then you can use this bialgebra morphism using this parameter alpha, and then get a deformed UQSL2, which has a Hom bialgebra structure. Let me just, of course, now with this structure, we can generalize all the results we have about algebra, about bialgebra. Then some alphas should appear there. But what we have here is also we can also have some challenging questions. And for what kind of cohomology we will have here. And for example, if we are interested in deformation theory, could we construct a cohomology which allows to deform both the product, coproduct, and the twist maps? This is, and then you need something more complicated. Of course, we had in some works generalization of Hochschild cohomology. Then in the coboundary map appears some alphas, which is expected. But we had also with one former student, Benedicto Urle, constructed a cohomology, the generalized Hochschild cohomology we called alpha type cohomology, where we have a complex where cochance contains two parts, one part dedicated to the multiplication and one part dedicated to the structure map. And within this alpha type Hochschild cohomology, we can control deformation theory where we deform both the multiplication and the structure map. Okay, then here maybe let me show you that also for bialgebra we can generalize we can generalize also this Gersten-Haber-Shake cohomology for bialgebra and get this alpha type Gersten-Haber-Shake cohomology for bialgebra, and the complex now is becomes more complicated because it involves the multiplication, the co-multiplication, and the two twist maps alpha and beta. And for coboundary, I'm not going to give you the definition of the coboundary maps, but just to state it like this, I mean, we have this, we have some delta mu mu, delta mu alpha, delta mu. We have eight maps defining this coboundary map for bialgebra. And if you want the relationship, I can. We are given here by this diagram. And if you take for associative algebra, the diagram is more is easier because you have d mu mu, d alpha mu, and you have only four arrows. Okay. Now let me talk about some categorical constructions with respect to this type of algebra. The first paper was about this, was done by Stef Kanepel and Goivert in 2011, where they studied this Hopf algebra from a monoidal point of view, and they constructed a monoidal category in which the algebra is a Hom-associative algebra. And this, then the construction is in this way. If you start with a monoidal category, then you can construct a new monoidal category, H delta C, which they call Hom category. And for this category, the objects are objects of C and an automorphism of this object. And then naturally, this category has non-trivial associativity constraint. And now, to get this Hom-associative algebra for C, one can consider the category of linear space over a base field K. And in this category, an algebra is something as a Hom-associative algebra. And the maps here are bijective. Okay, then now comes our collaboration with Claudia. I think she had the idea to generalize this Kanepel-Goivert construction. And she asked the student, Graziani, to do that, and she included me and Florian Panaiti in this project. And then we constructed what we call group Hom category. And here we start with a monoidal category C and a group G with two elements in the center and U an automorphism of the unit object of C. And then we have all this data. Then in this Hom category, group Hom category, the objects are pairs, AFA, where A is an object in C, and FA is a group homomorphism from G to automorphism of A. Then here, the associativity constraint is defined by means of all this data, and in general non-trivial. And we have also a braided structure on this group Hom category, which turns this category into a braided category. And now, again, we are going to take some particular case. And of course, if we take as a particular case G to be Z, D to be 1, and mu to the identity on 1, then what we get here is exactly the construction done by Kanepel and Goivert. But now, if we do something else, if we consider as G Z times Z, and here as C and D, these two generators, 1, 0, and 0, 1, and for new this identity of 1. And here again, we're dealing with the category of linear spaces. Then, if we have an M, which is a linear space, then we can define now a group homomorphism Fm from Z times Z to automorphism of M. These will be completely defined by their image on the generators 1, 0, and 0, 1, which we call the first by alpha M and the second one by beta inverse M. And here now an object in this category becomes a triple given by a linear space, and these two maps alpha M and beta M, where they satisfy some condition, and the associativity constraint here is given in this way, and we have also a braiding which is given in this way. Okay. Yes?
What's the role of C and D? Because you don't seem to be here. So is it in the tensor product?
C and D are elements here. this element.
What role do they play in the definition of the category? Maybe on the previous slide, in the general definition.
C and D C are the F. Here we are taking Fm of C.
Can you go back to the general definition? Where do C and D
Are in the center of G.
yeah, and how do they appear in the definition of the category?
The C and D, here we are defining alpha m, which appears here by the image of Fm on C.
Okay, so in the general case,
Yeah. And we are defining beta m inverse to be the image of your Fm on D.
and then they enter in this.
And they appear here, of course. You have this alpha x and the alpha beta inverse.
But you didn't tell us what the tensor product is. You're giving us the associativity constraint, but you didn't tell us what the tensor product is of objects.
This is the usual tensor product on vector spaces, on linear spaces.
But you have pairs, right? The objects are pairs
Yes?
or triples. Okay, go ahead.
I don't understand the question.
Just as you have pairs, so
Yeah.
what's the tensor product of triples? What is the tensor product of two triples? What triple do you get? It's going to be n tensor n, but then you have to do something with alpha and beta.
We are applying here the associative, the pairs are here. We are applying to, we take 3 pairs here, this pair. This is the associator of these three pairs, 3 triples, sorry. And again, we get the same here. Okay?
Yes, but I think his question is, what if you take 2 triples, so you take x tensor y, but what are the alpha and the beta of the tensor product?
Yeah, but this is usual. I mean, if you have X tensor M, this is tensor vector space, and tensor alpha M, which are maps here. Okay. Now this was. We can discuss later if you want. Huh? If it's not clear. Oh. Oh yeah. Okay. Yeah. In fact, this was a motivation to introduce this bi-Hom algebra. Then, as was done in the paper by Steph and Goivert, the algebra in the category was this Hom algebra, and in this category, the other algebra are bi-Hom algebra. Huh? Okay. We have 2 maps, and what a bi-Hom associative algebra now is if we arrange things to get a definition. Now the associativity is twisted by 2 maps, alpha and beta. Huh? Okay. Then on the left we apply alpha, and on the right beta. And morphisms are defined as usual, and the unitality is also here uses left and right alpha and beta. Okay? Again, we can define what bi-Hom Lie algebra is, and now the bi-Hom Jacobi is quite complicated here. It involves alpha and beta, and the skew symmetry is no longer the usual skew symmetry, because it involves also some skew symmetry which involves alpha and beta here. Huh? And the commutator now to lead us from bi-Hom associative algebra to bi-Hom Lie algebra is defined in this way. Huh? Okay, and Yao twist works as well. What we need here, we need two algebra linear maps, alpha and beta, and then construct, starting from an associative algebra, bi-Hom associative algebra by commutation, by composition, as we did before. Now again we defined we defined left a model here, and then since bi-Hom associative algebra is a quadruple here, defined by vector space, multiplication, and 2 structure maps, an A model over this A is a triple divided by triple where we have a linear space, and again 2 maps here, 2 endomorphism of M satisfying this condition. This is just a compatibility condition, and the usual condition is twisted here by alpha and beta, alpha on the left and beta on the right. Okay? These morphisms are quite natural. Now maybe I would like to show this construction, which is interesting. If you start with an associative unital algebra and you fix 2 elements in E, which are invertible, then you can define by conjugation with these elements 2 maps, alpha tilde and beta tilde, and then you define a new product, mu tilde, in this way, and then you get a unital biholm associative algebra, and this can help to characterize the representation. Then to have an A model, this is equivalent to get a morphism of biholm associative algebra between A and E, where E is this endomorphism of M endowed with the biholm associative algebra structure I mentioned before. Let me, I said that we have a series of papers with this quartet, Liu, myself, Menini, and Panetti, about twisting Rota-Baxter algebra, NS algebra, Novikov algebra, infinitesimal bialgebra, and generalized Rota-Baxter algebra. I would like just to mention this generalization of associative Young-Baxter equation. This is, was given by Marcelo Aguiar. And here we deform or modify the definition, and what we get here, this AR equals 0, this is the biholm Young-Baxter equation. And if you have a solution of this biholm Young-Baxter equation, for example, then you can construct a twisted Rota-Baxter operator. Then twisted Rota-Baxter operator is an operator satisfying this condition, and it is also very important in combinatorics and normalization theory, for example, in quantum field theory. And we defined also this infinitesimal biholm algebra. 1 minute? The extra minute when I answer the question.
You already had it. Okay. 1 minute.
1 minute, please. Yeah, just finish with this infinitesimal bialgebra, biholm bialgebra. This is the definition, and we have the characterization. Then, if we start with biholm Pareille algebra, with infinitesimal biholm bialgebra, we can construct biholm Pareille algebra, and we have this quasi-triangular infinitesimal biholm bialgebra, generalizing the works in a natural way, and maybe I can end with the characterization. If we have a quasi-triangular infinitesimal biholm bialgebra, then we have these 3 conditions, and then any infinitesimal biholm. If we have an infinitesimal biholm bialgebra satisfying the 3 conditions, then this is a quasi-triangular infinitesimal biholm bialgebra. Thank you very much. I'm so sorry for that.
Thank you. There are questions?
Your construction with the alphas and the betas now depend on a group, so the group homomorphism reminds me somewhat of the notion of equivariantization of a category in the concepts of in the book of Etinghoff, Delaki, Nixis, and Ostrich. Is there a relation between this?
I don't know.
You don't? Okay.
there are more questions?
Thank you very much, Nazar, for very interesting talk and very interesting results presented. I just have a question. Here in this by-home situation, when you have these maps alpha and beta, you are requiring the commuting. First of all, where really this condition becomes important, the commutativity of alpha and beta in this by-home construction, because you always include that alpha and beta must be commuting maps. And the second question, which is related to this, suppose you take these two maps, alpha and beta, and you start taking special cases like making beta to be alpha or power of alpha or polynomial in alpha, or, where obviously they satisfy your condition commutativity. So basically, if you try to see what happens if actually you don't have beta, but you have you just have dependence on one map, but still satisfying your commutativity conditions. One is where commutativity actually really needed, and the second is what happens if you just take limiting cases of one of the maps into the commutant of the other maps, or in say, yeah, in something.
Yeah, I mean, of course, we use this commutativity of maps in order to simplify things. Otherwise, it becomes too complicated. You cannot do anything. I think it's a good condition. Otherwise, we get stuck in calculations. Now, about particular case for example, for bi-home associative algebra, if you consider alpha equals beta, then you are in the home case. Huh? But not for Lie, for example. Then it's more tricky. If you put alpha equals beta, then you don't get exactly home Lie algebra. Then we have some notion about left home Lie algebra, right home Lie algebra, which are equivalent in some cases.
Okay, thank you. I'm afraid we have to stop here because the next speaker should start to present. Thank you very much, Nasser.
Thank you.
Let's have the speaker again. This morning is Francesco Sala, and he's gonna say us some information about homological whole algebras, quantum groups, and their categorification.
Okay, thanks. And let me thank you, the organizer, for the opportunity of being here. It's my first time in Ferrara. So, okay, what is the goal of my talk? So the goal of my talk is the following. So I would like to explain a machinery that takes spaces in algebraic geometry, moduli spaces, and these cohomological algebras we can see at the moment as a black box, and produce examples of quantum groups. And then if I have time, I don't think I will have time, but we will see, you can also categorify. So there is a machinery called categorified all algebras that takes spaces in algebraic geometry and produce a categorified object. So now, as you may see, this could be seen as orthogonal to the main topics of this conference. And so I would like to start with a very basic example in order to see where we are going. And so the basic example is this one. No. Too fast. So I want to consider an example of a shuffle algebra. So we take R as the algebra polynomials into variables. And then I want to consider the R module given by the direct sum of symmetric polynomials in the variables T1, Tn with the coefficients in R. Okay. And then I want to define a so-called shuffle multiplication on this vector space. So we take two symmetric polynomials. Obviously, the product of two symmetric polynomials is not symmetric. So I have to apply the così? Altrimenti anche senza magari, tanto per il uguale.
Poi non si sente in diretta.
Okay. Okay, it's fine. Maybe, okay, let me see. I'm very sorry. Now it's better? No. Now? Okay. So, as usual, if you take two, no. Okay. I'm very sorry. So, as usual, if you take two symmetric polynomials, the product is not symmetric, so you need to apply the symmetrization operators, but what we do is, before applying it, we multiply by these products of zetas, where zeta is exactly this function here. And now, this is an example of so-called the shuffle algebra, in which, again, you take some vector spaces given by symmetric polynomials, and before applying the symmetrization operator to define a multiplication, you multiply P and Q by a fixed kernel, this is called the usually kernel, that is that product of zetas by varying of ti's and minus tj's, where zeta is that one. And now, the idea is, okay, this since I hope it's very simple, it's very combinatorial, and then the idea is that I want to sell is this is exactly, so we take the so-called shuffle, but we do not by shuffle the subalgebra generated simply by powers of T1. So this means that the shuffle is generated by elements that are T1 to the K, and I multiply by the shuffle product by T1 to the L, and so on. And then the slogan is that this is an example of cohomological algebras. So now if you remember the picture before, what I was trying to sell is cohomological algebra is a machinery that takes a space and produces an algebra. Now you see the algebra, so I should tell you what is the space that we consider an algebraic geometry in order to produce this algebra. So this is the next goal. So again, the algebra is this one. So let me show you again. So I will be very slow, hoping that this makes things more understandable. So again, is as a vector space are symmetric polynomials, infinite many variables. And then the product is the usual shuffle product, but modified by this fixed function z. And now let's see what is the space that I should consider. So now I should fix what is the geometry. So what is the geometry that will give rise to this shuffle? And so the geometry arises with the so-called commuting variety. So what is the commuting variety? Is simply the set of matrices that commutes. And then I labeled the commuting variety by n, that is the order of the two matrices. So I take two matrices, and I take the set of matrices that commutes. So now, these sets has two natural actions. So the first one is an action by GL. The general linear group acts by conjugation, right? And then also I can act by the torus C star times C star by scaling the matrices. So the vector space that now the cohomological algebra, and this will be the cohomological algebra associated with the so-called one-loop quiver, but I will return back to this later on, is as a vector space simply the dual of the equivariant compactly supported cohomology on the commuting variety. So this gives me coa Tn, and then I take the direct sum all these vector spaces. So before we had a direct sum of symmetric polynomials in n variables, right? And now what I'm saying is that now we have a direct sum of vector spaces that are equivariant, okay, it's the dual of equivariant compactly supported cohomology of a variety of matrices that commutes. So what is the relation between the two descriptions? So the relation is at the level of vector spaces, one embeds in the other one. So this gives you a first hint of what could be the relation between them. And now, since there is written whole algebra, I should tell you what is the multiplication that I should define on the vector space coa T in order to match the shuffle multiplication that you saw in the slide before, right? So in the slide before, there were symmetric polynomials, and here we have dual of equivariant compactly supported cohomology of the variety of matrices that commutes. And before there was the shuffle multiplication, I should tell you how you realize geometrically the shuffle multiplication. So I hope more or less you are still following me. So again, the remark tells you that at the level of vector spaces, you can see this cohomology, again, it can be described as a symmetric polynomials. So great. And now, what is R is the equivariant cohomology of a point with respect to the torus C star times C star. Because before R was polynomials in epsilon 1 and epsilon 2, I identified them with the cohomology, the equivariant cohomology with respect to the torus at a point. Now, the whole multiplication is defined the following way. So this will be the next. So I needed to define a map that goes from coa T labeled with the integer n1, tensor coa T labeled with the integer n2, to coa T labeled with the integer n1 plus n2. Now the definition is completely geometric, and this use the two maps that I'm going to define, and so the multiplication is always given by some pullback with respect to a map Q, and a push forward with respect to a map P. Now, from one side, so, yeah, I needed the mouse. So the multiplication should go from the left-hand side to the right-hand side, right? There is only one way to go from the left to the right. I have to go up to the compactly supported cohomology of com tilde, and then go down by push forward to the right. There is only one way. From the left to the right, you have to pull back and then push forward. And this is what is written here. Now, what is this com tilde? It's simply, these are matrices, pairs of matrices that commutes of order n1 plus n2, and then we intersect it with a parabolic that fixes Cn1. So this is what is the definition, but maybe you would like to see at the level of matrices what's going on. So if I have two matrices that lives in this com tilde, you can write down as block matrices. And the fact that A and B were commuting will imply that A1, B1 and A2, B2 will commute. And so at the level of matrices, what I'm simply doing is that AB goes to AB on the right, because I'm simply taking matrices that are that were already of this order, and I'm going here, so simply this is the inclusion. And the map Q, what simply does is that takes the description as a block description of the two matrices and send A and B to the components of the block matrices, A1, B1, A2, B2, okay? And so now this is the definition. So everything is completely geometric. So again, what is the point here? The point is that in the first slide, I gave you an example of what I call shuffle algebra. This was completely combinatorics. It was a vector spaces given by symmetric polynomials with a multiplication in which there was symmetrization operators modified by a fixed function. And now I'm telling you the idea that this can be also realized as some cohomology of a very simple space, the space of matrices that commutes, and the multiplication is given by pull back with respect to the map Q, push forward with respect to the map P. Again, the map Q takes A and B and sends them to their components, the diagonal components, and the map P, now there is this thing that is blocking it, the map P sends AB to itself. And now what's going on here, so this is an important theorem by Schiffer and Vassereau. So first, indeed, M induces a unital associative algebra structure over the vector space Coa T. And the second thing is that from one side, Coa T, this is a non-trivial theorem, can be described as the shuffle that I showed you before. So that subalgebras of an algebra of symmetric functions. On the other hand, there is a connection to quantum groups. So before I was telling you that cohomological algebras take a space and produce a quantum groups. And in here you may see an instance of what Andrea Appel was telling us 2 days ago. So Coa of T indeed realized a positive part of the affine Youngian of GL1. And so this affine Youngian of GL1, as Andrea was telling us last time, has a triangular decomposition, and Coa T realized geometrically exactly one part of it, the Y plus. Now, when I say that this Y plus part of the quantum group is realized geometrically, it means for me that both vector space as an interpretation as, in this case, cohomology of some space in algebraic geometry, and also the multiplication arise geometrically via the maps that I described before. Now, as Andrea was telling you last time, Youngians appear as deformations of current algebras. And here is a current algebra of a Lie algebra that is called the Maulikov-Kunkov Lie algebra of a one-loop quiver, and then I will say more in a few minutes. So this is the reason that it's called Youngian, is indeed a deformation of the universal enveloping algebra of a current algebra, as in Andrea Appel's talk. Moreover, this is a topological off algebra, where the topological comes from the fact that you need the coproduct is only at topological level. And this was defined in two different ways. One way was defined by Maulikov-Kunkov by using the R matrix that you already saw in Andrea's talk. And their definition was again in a completely geometric setting. And there is another definition given by generated relations by Schiffer and Vassereau. How this description arise? So you have presentations given by polynomials, symmetric polynomials, and then you start computing relations in this very combinatorial presentation. So the outcome of the talk is, at the end of the day, these cohomological algebras, they have always a combinatorial flavor that allows you to compute explicit relations. Okay, and now, always in this story of cohomological algebras, for those of you that maybe saw before and so on, so this gadget already realized half of the interesting quantum group. So in order to realize, in this case, the full Youngian, you need to double it, which means you have to insert a Cartan, you have to define at least a bialgebra structure, and then take the, okay, this is okay, see. Okay. Unfortunately, this okay, this is what it is. So, and then you usually take the Dirichlet double in order to realize the full of it. Okay, so again, what should remain from this first 15 minutes of my talk? Remains the following. So I presented a very, I hope a very simple algebra that was an algebra of polynomials, symmetric polynomials, with a product that was given by applying the symmetrization operator modified by some fixed function that I call kernel. And then I solved the idea, obviously it's only the idea, that this very explicit combinatorial gadget can be realized by using geometry, where the geometry enters in the vector space because the vector space is some cohomology of some simple variety, the variety of matrices that commutes, and also the multiplication is given by some geometric terms via maps that I defined before. Now, let's see what, as I said before, this fine Youngian of GL1 is only one example of a family of Youngians that indeed were defined by Maluk-Okunkov. And so Maluk-Okunkov defined the following. So starting from a quiver, which is simply an oriented graph, and I denotes the set of vertices and E the set of edges, they produce an R matrix, and out of this they produce a gigantic beast that is this Maluk-Okunkov Youngian, which is a graded off algebra that is a deformation of some current algebra. And then when this G, the Lie algebra, is again a graded Lie algebra, and this degree 0 part with respect to the Z grading is the usual Kac-Moody Lie algebra of Q. Now, why Maluk-Okunkov wanted to introduce this guy? So, as you saw before from Andrea's talk, when you have a thinking diagram of finite type, already Drinfeld in 1985 defined a Youngian. Then his definition can be generalized for any quiver without loops and without loops. But then there are a lot of interesting examples that arise when you start to insert loops to a quiver. For example, before I provided you what you will see now in a second is the example of the very stupid quiver with a loops, one vertex and one loop. But already in this case, in which you have one vertex and one loop, I tried to sell you the idea that you get something very, very interesting. And so Maluk-Okunkov's goal was, one of the goals was to say, what happens if we start to decorate our quivers with a lot of loops? Okay, there is another point that maybe I should say. I have still 12 minutes, I guess. The 12 minutes? Okay, great. Is that for those of you that are familiar with Kac-Moody algebras and so on, there was this old conjecture of Katz that was telling you that the graded dimension of the Kac-Moody algebra was governed by its polynomials, the so-called Katz polynomial. But was governed only the constant term of this polynomial was providing the graded dimension of the Kac-Moody algebra. And this was like 30 years ago. And for a long time, people were saying, okay, so I have a polynomial, whatever this is, and the constant term has a Lie theoretic interpretation. What is the Lie theoretic interpretation of all the other coefficients in this polynomial that Katz constructed? And indeed, this is the Maluk-Okunkov Lie algebra provides a Lie theoretic interpretation of this polynomial by Katz because this graded dimension is governed by this Katz polynomial. This was one of the motivations of Okunkov of also introducing all this machinery. Now, what is the relation between this case and the previous one? So the previous one will be the case in which the quiver is one vertex and one loop of it. So very simple, I hope. So in order to establish a connection, I should show you that indeed the commuting variety has something to do with representations of the one loop quiver. And so I start again with the two matrices. So I have two matrices, and I can see them as endomorphism of the vector space Cn, and they also commute, right? Great. So now there is a little fate. They corresponds to the dimension here is n, to an n-dimensional module with respect to the so-called preprojective algebra of the one-loop quiver. What is the preprojective algebra of the one-loop quiver? So you take your one-loop quiver that has only one loop, x. You double it, so you double the loop. You have x, another loop, y. And then you impose the commutation relation that goes under the name of preprojective relations. So in this case, you simply get an algebra of polynomials in the two loops x and y. But obviously, this can be generalized. And so again, when you have a quiver, the projective algebra will be a certain quotient of the path algebra of the double quiver, where double means that you are doubling the errors and also reversing the orientation of the new ones. So what remains here of this story remains that what I'm trying to tell you is, starting from two matrices that commute, they correspond to a module of a certain algebra that arises from as a quotient of some path algebra associated with the one loop quiver. Okay? And this is algebra is called the preprojective algebra of this one loop quiver. And now, if you take quotients with respect to GLN, this quotient in the category of stacks, but let's forget about this, it's exactly the space parameterizing all these modules. So all the modules with respect to these algebras are indeed given by A and B. And the fact that I have to mod out by GLN is because if I change my basis in Cn, I should not change what is the module. This is the only reason. So this is the commuting variety. But in my diagram, there was also the com tilde. So what is the com tilde that I introduced before? So the commuting variety gives rise to modules over this preprojective algebra, and simply com tilde gives rise to extensions of modules. So com tilde simply gives rise to extensions of modules where M is a modulo of dimension n1, and 2 is a modulo of dimension n2, etc. And the maps that I defined before, P and Q, what do? They take a short exact sequence and they send, P sends the short exact sequence to the middle term, M n1 plus n2, and Q sends the short exact sequence to M n1, M n2, so to do a stream. So before I gave you a description in terms of matrices, but now you may see that everything, at least from my point of view, is very geometric, because matrices up to conjugation it corresponds to modules over this preprojective algebra, and then com tilde corresponds to shortest subsequences of these modules. And so what I showed you before is exactly, can be rephrased in this way. So simply I take the cohomology, completely supported cohomology of the space all the representation, finite dimensional representation by varying of n. And then the multiplication is the one that I defined before. Before was given in terms of matrices, now it's given in terms of maps that sends a shortest subsequence either to the middle term or to the extreme terms. Okay, now I imagine that is already, I have 6 minutes left. So it's very intense until now, I imagine. So now what should remain from this? It should remain that a priori I start with some nice space. In this case, it's a space of finite dimensional representations of some quotient of some path algebra of a quiver. I endow this vector space by some multiplication. And in this way, I define an algebra that has both a combinatorial flavor and has a relation with the quantum groups. And obviously, you can replace the one loop with any quiver, and you get again the same result as before. And so again, this COA associated with Q is an associative algebra, and it realizes geometrically 1/2 of the Malichov-Kunkov-Yangian. And again, as before, quivers are combinatorial, and then also this COA has a shuffle algebra interpretation, so you can give it as some polynomials, symmetric polynomials, with again a multiplication that will depend on some kernel. So why we like all of this? So at least people like this because it provides a different interpretation of Maulico-Kunkov-Yangian, but moreover the point is that, as I'm trying to stress a lot, COA provides you a way to define generators, and so in this, thanks to this, you can really compute also relations in all the cases described before, also in the cases described by Andrea 2 days ago. So Mauri-Kokunkov description is given simply by R matrices, but it's nice to have representations by generator relations, and the cohomological algebra provides a way to do that. And so now what we can do? So a priori there is no need to only consider cohomology. We can also consider K-theory. So we can consider the Grothendieck group of coherent sheaf, and then by passing to K-theory, you get the K-theoretical algebra, and the Youngians are replaced by quantum loop algebras. So cohomology corresponds to Youngians, corresponds to current algebra. K-theory corresponds to loop algebra and quantum loop algebras. Okay? You can also use other cohomological theories to get other stuff, but let's not get into this. And so, what could be an interest in doing this? No, right? So Schiffman and Vasserot provides an interpretation of this Mauri-Kokunkov Youngian that extends the usual Youngian of Drinfeld. So one can say, okay, what's next? And so the point is, now the machinery is very general. So the machinery is so general. I have what, 7 minutes? No, why 2? I started at 10. So. Yeah, you're right. Yeah, okay, it's impossible in 3. Okay, now you have check again, it's impossible. Okay, now it's impossible to say what I want to say, so let's try to say something. Or I can do like the other speaker and say, there is next slide, and then I will continue. So, what can I do? What I want to do is now, I provide a machinery that works for a specific space, that is the space of representation of a quiver, but I can replace with another one and produce new families of Lie algebra, new families of Youngians, new families of quantum loop algebras. Okay, so how I do this? So for example, a result that I have with Olivier Schiffman is that we can take, for example, the space of properly supported coinecies on S, on a smooth quasi-projective complex surface, and then again you can get a cohomological algebra associated with it. And then when you pass to K-theory, you can get a K-theoretical algebra. Now, since I don't have time, I will say in a few words what we also proved. So this is very abstract or very like, I don't know. So one say, okay, so you have a machinery to produce an associative algebra, but then what is really this associative algebra? What is its structure and so on? So for example, among all possible surfaces, a very simple one is a minimal resolution of an ED singularity. For example, I take Z2, acts on C2, I resolve it, is the cotangent of P1. And so I can take a cohomological algebra associated with the cotangent of the projectile line, and one can wonder, what is this guy, right? So by McKay correspondence, I think that what should appear should be related to the Dinkin diagram of tape A1. This is indeed the case. So if I plug in, instead of S, I plug the cotangent of P1, I indeed get an half of the Youngian, the affine Youngian of SL2. But the point is that the half that I get is not the one that Andrea was describing, it's a new one. So already, if I plug the cotangent of P1, this is a work in progress with infinitely many people, Diaconescu, Porta, Schiff and Vasserot, since we are recording, let's mention them. Since in this case, already I use, if I use a very simple, the cotangent of P1, then what I get is, okay, I get an half of the affine Youngian of SL2, but it's a new one. Instead of P1, I can take, I'm finishing, I can take an elliptic curve, and in the case of the elliptic curve, and this I want to show, yeah, I'm playing the same game that was played before, I'm very sorry. So in the case of the elliptic curve, what one should get is the Youngian of GL1, but not affine, but double affine. So this guy does not exist. So this guy has no definition in the literature. So it's something that people in physics have speculated that it exists, and this should come from the quantization of this current algebra here. And if you pass to K-theory, then you should see here UQ with the free hat in K-theory. Both things do not exist, and so the point here is that we use geometry and we use the fact that this exists, I define it with Olivier Schiffman, to provide a description by geometric relation and eventually have a way to define this beast. So this is, at the end of the day, this is the goal of this program. The goal of this program is create new Youngians, new Lie algebras, new quantum groups in general. And obviously we can categorize all of it, but I have no time, and so thank you.
Thank you.
There are questions?
So can you say something about categorification? What do you categorify? And
yes, I can say by showing the slide. It's the easiest way. So the slide is technical, so let me say in this word. So for me, categorification means the following. So what is the category? The category is a triangulated category, or more precisely, it's a stable infinite category, because one has to work in derived algebraic geometry. And then you take the map that I showed you before. I was telling you that you do pull back and push forward. So you do in dual compactly supported cohomology, you do in K-theory, you can do in Chow, you can do in elliptic homology, and I do here at the level of bounded derived categories. And this provides a monoidal structure. Now, the fact that here it is written E1 is because the monoidal structure does not depend only on the diagram that I showed you before. That diagram, but it depends only on the iteration of this diagram, because I can take a shortest subsequence, I can take a shortest subsequence of a shortest subsequence, and then I can iterate. All this iteration is codified by this word. And so again, the category is a triangulated category, or a DG enhancement of it, and the structure is a monoidal structure, but in this sense, E1 monoidal, in which the monoidality takes into consideration all infinite many higher associativity conditions, not only the first one.
I just have a technical question. So if how properties of this quiver are reflected in the properties of corresponding Hopf algebra or corresponding algebraic structure which you define, in the sense of, for example, if you have a tame or wild quiver, or if you have is there any special property of those algebraic objects which corresponds to a specific types of quivers? Or
so, for example, if the quiver has no loops, I mean, okay, I will try to give you an answer. I don't know if this will be satisfactory. So if the quiver has no loops, then at the end of the day, for example, if it's Dinkin, so it's a Drinfeld-Yangian, and the Lie algebra is the usual Lie algebra associated to the AD quiver. Now, when you pass already to a fine ADE, it's a little bit bigger, this Manuel-Kokunkov. It's some central extension of it. But then the point is that you will see, so, I mean, from my point of view, the interesting part arises when you have loops. Because when you have loops, you have that the root space is no more one-dimensional, and there is a long program by Schiffman and the students that try to describe what are the root spaces in this case. Now I will tell you some keywords, I will tell you in this way. That is, in these cases, what happens is that somehow these root spaces should be related to cuspidal functions for quivers. That should be the quiver analog of cuspidal functions for curves. But this it's something that they are able to define, although, I mean, it's cuspidal because they call in this way by analogy with the curves. So the loops gives you all of these extra, let's say, automorphic force, but
let's say for the quiver.
No, I have a very silly question, but somehow in the picture I have in mind, I'm not Youngian or affine, I mean, I'm in a finite case. But then what you would have is that the shuffle algebra is the positive part of the, I mean, the positive part of the quantum group would not be the full shuffle algebra, but would be a smaller
that
thing.
one that was generated
Yes.
by T1 to the K.
Okay, so this is the picture you also have here. Okay.
Yes. So then you may also describe the same thing by, you can say that is the subalgebra generated by T1 to the K, or now again as before I will say you keywords, is the subalgebra of a symmetric polynomial that satisfy the so-called wheel condition, that are some conditions, some equations that this polynomial satisfy. And that's it. So again, this condition, I mean, there are two equivalent ways. So it's one of these, and the other one is, these are the polynomials that satisfy these equations. So this is the idea. And you can also do the shuffle algebra at the level of K-theory, and instead of taking T1, T2, Tn is T1 plus or minus 1, T2 plus or minus 1, and the zeta function is no more additive, it's multiplicative. So anytime you see minus, I mean, it's multiplicative.
There are more questions? Okay, it's time for one more question. You have one?
So it is natural to define the comultiplication in this object that you define it geometrically?
It's very challenging. So in the case of quivers, yes, you can do. And what you do is you take the diagram that I showed you before, and you go from the right to the left. So the diagram at the beginning is the one with the matrices and so on. So the commultiplication is only topological because you have to complete the tensor product. Modulo all of this. The only thing that you do is that, okay, I'm going there. Let me go there so I can show you the diagram. Okay, this is not so fast. This, or maybe my PDF is gigantic, one of the two. It's going there. I'm very sorry, it's coming, it's coming. Unfortunately, I cannot write on the blackboard. So maybe it will crash eventually. No, here, stop here. So you go from the right to the left, and then in this way you define the coproduct. In the quiver case. In the case that I'm considering in which you replace the stack or representation of a quiver with some more complicated spaces, is an open problem that some people, for example, Davison and Edinburgh, stated that it is solved, but at the moment there is nothing available, but maybe eventually will appear. So, and anyway, it's always geometric. You go from the right to the left, this is the way that you do.
But is your coproduct is the same Monoidal coproduct?
The idea, I don't think that this was checked by the people that proved. Okay, so let me put a context in the question of Andrea Appel. So Maulik-Okunkov define an off-algebra structure. How do that? They fixed a representation coming from geometry. They define an R matrix geometrically, and then they use FRT approach to define an off-algebra. Then the problem is that, yeah, great, but then what do we do with that? So all this program of these people is to write down explicitly what's going on and what is the coproduct. That is very important. The coproduct, for example, in the case of a loop quiver is written explicitly, and in the case of affine quivers as well. But then in general, I mean, when I told you pull back and push forward, great, but then explicitly in only certain cases you can write down what's going on. So conceptually you have it, but explicitly it's complicated to write down formulas in which you see the coproduct evaluated to some generators and what is the expression. This is a challenging part. So
thank you.
Okay, so we have to stop here, maybe to continue the discussions during the coffee break. So we have to be back at 20 past 11. The next talk will be at 25 past 11. In case that somebody wants to leave the luggage here, he or she can do it. So to don't carry the luggage to the place where the coffee break takes place. Okay, let's start. Our next speaker, we agree, is Margaret from Poland, and she will gonna speak about Hopf braces, Hopf trusses, and Hopf hips. Please.
Okay, thank you. First, I would like to thank organizers for the invitation to the conference. I'm glad to be here. The title of my talk is Hopf braces, Hopf trousers, and Hopf hips. Wolfgang Rump answered the question of whether there is an algebraic structure consisting of two binary operations interacting with each other in which all elements are invertible with respect to both these operations. This structure is called a brace. Following to Rump, a brace is an empty set. Together with two binary operations, the addition making the set B into an abelian group, and multiplication making the set B into a group. Both the operations are required to satisfy the brace distributive laws. The surprising thing is that in a brace, both the additive and multiplicative neutral elements are equal. And we have an example of a brace. The set B is a brace in which the cycle group of order 4 forms the additive structure and the Klein 4 group forms the multiplicative structure. In a skew-left brace, we don't require groups to be abelian. Left means that only the left brace distributive law holds. The notion of a skew-left truss generalizes the notion of a ring and a skew-left brace. In the definition of a skew-left trousers, we have a so-called ecocycle, and ecocycle is 0. If ecocycle is 0, then we have so-called left near ring. And if ecocycle is unit, then we have a skew-left brace. This definition of a skew-left truss is impractical. The next theorem somewhere confirms that the previous theorem can be reversed, but let's now pay attention to the notion of a skew-left truss, because in the definition of a skew-left truss, for us, the K notion is a hip. Following Heinz Prover and Reinhold Beer, a heap is an empty set with a ternary operation denoted by the bracket, satisfying the heap associative law and the Maltsev identities. The heap associative law allows us to move the bracket only from one end to the other. We can't put the bracket in the middle. And we have an example of a heap. Consider the set of integers and define the ternary operation on it, like on the slide. We obtain a heap. The first theorem says that every group gives rise to a heap, and the second theorem says that starting with any heap, we can assign a group to it by fixing the middle entry of the ternary operation. A heap can be understood as a group in which the neutral element hasn't been specified. A choice of any element in a heap can reduce the ternary operation to a binary operation that makes the underlying set into a group in which the chosen element is the neutral element. And now, let's move on to the Hopf structures. If we look at the definition of a skew-left and think about a group algebra, then we can easily see that the relationship between the two definitions, the definition of a skew-left brace and the definition of a left Hopf brace. A left Hopf brace is a coalgebra with counit, together with two binary operations, making the coalgebra into two Hopf algebras. Both the operations are connected by the left Hopf brace distributive law. Okay, and we are not surprised that both the units are equal. And there is a proof on the right. An example of a left brace. Consider a skew-left brace G. For our convenience, the definition of a skew-left brace is on the slide. Both the binary operations make the vector space generated by elements of the set G into Hopf algebras. So, as a basic example of a left Hopf brace, we may take the group algebra of a skew-left brace. The next example of a left Hopf brace. If we take a Hopf algebra with the antipode, which in the second power is the identity, then also the opposite algebra is a Hopf algebra. Both the Hopf algebras are connected by the left Hopf brace distributivity. The notion of a left Hopf truss generalizes the notion of a left Hopf brace. But the definition of a left Hopf truss, which we see on the slide, is impractical. So, the theorem which we see on the next slide gives a much more practical characterization of the notion of a left Hopf truss. We can associate the ternary operation with a left Hopf truss. In the middle, there is co-opposite coalgebra. Yes. In ternary operation appears to be a coalgebra homomorphism. Moreover, it satisfies the Hopf-heap associative law, the Hopf-Maltsev identities, and the left Hopf truss distributive law. The next theorem somehow confirms that the previous theorem can be reversed. But let's now pay attention to the notion of a left Hopf truss, because in the definition of a left Hopf truss, for us, the K notion is a Hopf heap. So, in our joint paper, Tomasz Brzeziński and me defined the notion of a Hopf heap as a coalgebra with counit, which admits a ternary operation. The ternary operation is assumed to be a coalgebra homomorphism. It's required that the ternary operation satisfies the heap associative law and the Maltsev identities. Maltsev identities in a Hopf heap look little different those in the heap. The definition of a heap we have on the slide. For our convenience, and an example of a Hopf heap. Given a heap G, we can define the coalgebra structure on the vector space generated by G. The ternary operation on G makes the coalgebra with counit into a Hopf heap. A homomorphism of Hopf heaps is assumed to be a coalgebra homomorphism respecting to the Hopf operation. And the theorem on the slide says that every Hopf algebra gives rise to a Hopf heap by taking the ternary operation of the form like on the slide. This Hopf heap will be called associated to a given Hopf algebra, Every homomorphism of Hopf algebras is a homomorphism of associated Hopf heaps. And the next theorem. The theorem on the slide says that starting with any Hopf heap, we can assign a Hopf algebra to it by fixing the middle entry of the ternary operation. Element E has to be a group-like element of this Hopf heap. Hopf heap understood as a coalgebra. The assumption that E is a group-like element of a Hopf heap guarantees that E is a unit of the associated Hopf algebra. A Hopf heap can be understood as a Hopf algebra in which the identity element hasn't been specified. Choice of any group-like element in the Hopf heap can reduce the ternary operation to a binary operation that makes the underlying set into a Hopf algebra in which the chosen group-like element is the identity element. If phi is a Hopf heap homomorphism, then for any group-like elements E and F, the map phi hat defined on the slide is an associated B-algebra homomorphism. In both the Hopf heaps, if both the Hopf heaps admit the Grunspan map, the definition of the Grunspan map is on the slide. If both the Hopf heaps admit the Grunspan map, then the map phi hat is an associated Hopf algebra homomorphism. And corollary, if we take identity map as the map phi in the last theorem, then we obtain the corollary, according to which for a Hopf heap and group-like elements E and F, the map tau is an associated B-algebra isomorphism. If the Hopf heap admits the Grunspan map, then the map tau is an associated Hopf algebra isomorphism. In our paper, we proved, in fact, that every Hopf heap admits the Grunspan map. These theorems define process of going from a Hopf algebra to the Hopf heaps associated to it, and from a heap to the Hopf algebra associated to it. So, these processes can be composed, of course. Natural question to ask here is, what is a relation between a Hopf algebra we start with and a Hopf algebra we received at the end? The theorem on the slide proves says that when we start with a Hopf algebra, convert it into the associated Hopf heap, and then back to the associated Hopf algebra. In general, we don't obtain the Hopf algebra we start with, but we obtain the Hopf algebra isomorphic to the Hopf algebra we start with. And the same question in Hopf heap case. What is a relation between a Hopf heap we start with and a Hopf heap we received at the end? And there is the answer. We obtain the same Hopf heap we start with. And moment. Grazie mille per la vostra attenzione. And I would like to say that Hopf heaps are very, very young very young structure, so I don't know anything about it. More than what I said.
Okay, thank you. And if there are questions, please.
So, what about duality? So, take finite dimensional Hopf algebra. You know that the dual is also a Hopf algebra. You can produce heaps from that. And what about the dual of a heap? This is, of course, not a heap, but maybe. Does that exist?
I don't know.
There are more questions? Comments? No? If not, let's thank the speaker again. And we have a break of 8 minutes.
So I would like to thank everybody for coming here, and it was a great joy for me to host all of you in this meeting. But right now, my best thanks are to our technicians, Dr. Filippo Lantini and Stefano Droghetti, who made this meeting possible. And it seems that in the first day it was really followed. We had more than 150 contacts. How do you say? Log in to the YouTube channel. So thank you very, very much for your perfect work.
And maybe this is the right moment to thank also to the organizer again, to Claudia, to the people from Ferrara, from Turin, and across Italy to help in the organization of this beautiful conference. Okay. And now the next speaker, it's my pleasure to introduce Drago Ștefan from University of Bucharest. He will speak about the deformation theory on associative algebras. Thank you.
Okay. So first of all, thank you very much, Claudia and Alessandro and the other organizers for inviting me to attend this meeting and deliver a talk. And at the same time for the opportunity to visit this beautiful city once again. Thank you so much. Okay, so I'm going to talk about deformation theory of associative algebras. A short plan of my talk. First of all, I would like to recall the definition of formal deformation as it was introduced by Gerstenhaber a long time ago. And then I will present the framework of our approach to deformation theory. And the main bricks of our construction consists in two parts. First, a monoidal category that will come somehow in a natural way, and the main definition, the main notion that we use, namely I deformations. Finally, I will state the main results and discuss about some application depending on the time that it will remain. Okay, so first of all, some terminology and notation. K will be a field. If we have a vector space V, the set of all formal series with coefficients in V will be denoted by V sub T. Always M will be a K linear monoidal category. And as everybody knows, by an algebra in M, we mean an object A together with some multiplication which is associative. But be careful, in general our algebras have no unit. There is a, say, philosophical reason to omit the unit, because in deformation theory, usually deforming something which is unit is automatically with unit. This can be made precise, but I don't want to go into details. Okay, so what a deformation is? To deform an algebra AM, as above, here, for this part of the talk, M is just the category of vector spaces. So to deform an algebra means to extend the multiplication to KT algebra structure on AT, on the ring of formal series, of course with respect to the Cauchy product. Okay, so we might try a naive approach to look for KT linear maps from AT tensor over KT by AT and going to AT. Usually we are not so lucky to get the answer from the first attempt. So actually what we have to do is to complete the tensor product and then to work with algebras in some monoidal category that contains complete KT modules. One of our goals is to get rid of this mess about completion, topology, and related things. And the way to do that is to construct a certain category. But before doing the construction, let me show you an equivalent way to define a deformation. And this is what you will find reading the papers by Gerstenhaber. So, a formal deformation is a map, K-linear map, M prime, from the tensor product of A by itself and taking values in AT. Therefore, M prime evaluated at a tensor monomial A tensor B looks like a formal power series with coefficients in A. The coefficients being Mi of A tensor B. Of course, all MIs define some K-linear maps. And if the definition of deformation imposes that M prime to be associative, meaning that the family Mi satisfy the equation 1. And also M prime has to extend M, that is M0 to be equal to M. As I already said, our goal is to construct a monoidal category in such a way that deformations are algebras in that category. And the construction is suggested by the fact that we can regard M prime as a k-linear map from the vector space of polynomials in variable t with coefficients in k, and which take values in the set vector space of morphisms in M from A tensor A to A. Of course, the identification is given such that T to di goes to Mi. Okay, so it's the moment to introduce the category that we are interested in. We start with a k-linear monoidal category M, and together with C, with co-commutative K algebra, you might ask why C has to be co-commutative. The answer for the moment is that otherwise it will not work. And you'll see reasons for that a bit later. The new category MC has the same objects as M, but the morphisms are more complicated. The morphisms from X to Y are k-linear maps from C to the home space of morphisms in M from X to Y. We can expect that the interesting part of the construction is the composition operation. I will call it the convolution composition, and I think it's clear why. It looks pretty much like the convolution product in the theory of coalgebras. So, more precisely, if F and G are morphisms, as indicated on the slide, the convolution composition F star G is the composition of the three arrows on the last line, where delta, of course, is the co-multiplication of C. F tensor G is the tensor product of F and G as linear maps. And, well, the most right arrow is just the composition in M. The identity in this new category maps an element in the coalgebra, say little c, to epsilon of c Ix, where of course Ix is the identity of X in the category M. So this is the category that we shall use. Still is missing the monoidal structure, but this is what I am going to speak about. So the tensor product of two morphisms again looks like a convolution product, but now, well, F tensor F prime is as above, is the tensor product over K. On the other hand, the most right arrow comes from the monoidal structure of M. So there are some other things still to be defined, but I would skip the precise definitions because actually these structures like associativity constraint, unit constraints come from those in M via some identification of M as a subcategory of MC. More precisely, if we have a morphism of coalgebras, I from C to C prime, this morphism induces a functor, I star, from MC, it is a contravariant functor, from MC prime to MC, which acts as the identity on objects and I star of F is the composition of F and I. So using this functor, we can embed M inside MC, as you can see, and this embedding can be used to import the associativity constraints from M to MC. Okay. Having some monoidal category, we can speak about algebras inside that category. In our case, a multiplication is given by a k-linear map from C to that home space in M. And this M gives us an associative multiplication if and only if equation 2 is true. On the other hand, morphisms in the new category are given by some F from C to M of A and A prime, such that equation number 3 holds. We have objects, we have morphisms, so we get a category that I denote by AC. And I don't know, maybe I can go further to define deformations. So in our approach, a deformation depends on the category M and a morphism of coalgebra I as before. So the construction will be, the definition will be relative to a morphism of coalgebras. So by definition, a deformation is an algebra in AC star such that M prime composed with I gives you is equal to M. And as usual, if you want to classify the objects that you are studying, you have to identify them somehow. In our case, we define this equivalence relation. Two deformations are equivalent if there is an isomorphism in the category of MC prime, such that the last equation is true.
Travis, can you repeat, please, what's little I, small I?
I is a coalgebra morphism from C to C prime. Always it will be something like that. Maybe this diagram will help us to understand a bit better the definition. You see, we have M prime and I that make that triangle commutative. And what we are interested in, we want to see if such an M prime exists. I mean, you have an algebra M. Is there any deformation of M? Even in the case, even in the work of Gerstenhaber, the answer is no, in general. So we expect that things are even worse. And, well, supposing that there are deformations, how many there are? I mean, describe the set of equivalence classes of deformation. The diagram suggests you that the problems that we are trying to solve, it's a sort of lifting property for our structures. Okay, so how to recover the definition given by Gerstenhaber. It's enough to take I to be the inclusion of K inside KT, and it is not difficult to see that I deformations, in our sense, coincide with formal deformation introduced by Gerstenhaber and conversely. Here the coalgebra structure on KT is given by delta and epsilon on the last line. There is another situation that can be reobtained. Of course, taking polynomials of degree at most n, we get a subcoalgebra of KT. So it makes sense to take I, the inclusion map from K into KT into the set of polynomials of degree at most n. What we are going to do is try to extend as far as we can the results due to Gerstenhaber. And the right place to do that is working with coalgebra extensions. Coalgebra extensions were introduced by Doi many years ago, and the theory is well understood. A coalgebra extension is given by a morphism of, well, an inclusion, in this case, of coalgebras. So C is a subcoalgebra of C prime. We have to work with co-commutative coalgebras, and maybe I can tell you why we need the coalgebras to be co-commutative. This is because otherwise the tensor product that we defined on MC is not a bifunctor. So you need some commutations relations that do not hold if C is not commutative. Okay, so where? For the theory of extensions, the coalgebras might be arbitrary. For the construction of MC, you don't need to be. No, as a category. Yes. So the construction as a category works for arbitrary coalgebras, but when you introduce the monoidal structure, then you need co-commutativity. Okay, so by the general theory developed by Doi, we know that the co-multiplication of C prime can be reconstructed from that one of C and some other things. First, a right comodule structure on the co-kernel of I, C prime mod C, if you want. And, well, you need also a 2-cos cycle, denoted by omega here, of C with coefficients in X. I would say just that a 2-cos cycle is a K-linear map from X to C tensor S, C tensor C, satisfying some, some conditions. We are getting closer to our main results. So, by the work of Gerstenhaber, we know that deformations are controlled by Hopf homology of the algebra that we deform. In our case, the situation is similar. If we start with, if I is a coalgebra extension, then we can define a semi-cosimplicial set, C star of iota of I and M, where a co-simplex of degree n is in fact a K-linear map from X to that home set, home space. Again, the definition by the definition we recognize the definition of usual Hochschild homology. Having a semi-cosimplicial set, we get for free a complex.
X is the co-kernel of iota, yeah?
Sorry?
X is the co-kernel.
Yeah, X always will be the co-kernel of I. Okay, so from a semi-cosimplicial set, we get for free a complex, adding with a sign all cophase operators in the same degree. And the corresponding cohomology will be denoted by H star of I and M. So here there are our main results. Given an algebra in A, C, and I as before, we will denote by D of I and M the set of all deformations of M. In order to see if M has a deformation, we introduce a three cochain in our complex that we call the obstruction to deformation, and which is defined using the two co-cycle associated to the extension. So omega is used to give you the abstraction. Here I use some a Swidler-like notation for omega. The theorem is the following. First of all, the abstraction is always a co-cycle, 3 co-cycle. There is a deformation of M if and only if the abstraction is trivial. It's a boundary. Well, assuming that we have, there are deformations, meaning that the cohomology class of the abstraction is trivial, then the equivalence classes of deformations are classified by the second cohomology group. So there is a one-to-one correspondence between the set of equivalence classes of deformations and H2. What? Good. Too much. I hope. What about applications? How to recover Gerstenhaber's results? It's enough to take I to be the inclusion of these two coalgebras. So the domain contains all polynomials of degree at most n-1. The other one contains polynomials of degree at most n. You recognize the coradical filtration on KT. So actually, here we work with the coradical filtration on the coalgebra KT. So in this setting, we can recover some of Gerstenhaber's results. But there are some new applications, such as multi-parameter deformations. Instead of working with polynomials in one variable, we can look at polynomials with R variables, and we can get similar results. So in particular, we get that description of the set of equivalence classes of deformations, which now is in one-to-one correspondence with that H2 at n, to the n, where n, of course, is the dimension of the space of homogeneous polynomials of degree n in T1, Tr. Okay, so we can look also at deformations of families. Up to now, we fixed some multiplication and try to deform it. Now we can start with a family of multiplications, MS, which are indexed over a set of group-like elements in C. And in this case, we have also a result in which we can we classify the corresponding deformations. I would like to mention that all previous applications are somehow particular cases of a more general result in which the comodule X can be written as a direct sum of one-dimensional comodules. And well, here it is the result in the most general situation for deforming families of multiplication. Okay, thank you so much.
Okay, if there are questions, he was first and also I will bring the microphone.
Maybe I have to...
So, in your cohomology theory, of course, if C is trivial, then you recover Hochschild cohomology. What happens if A is trivial? Namely, if you take the unit object of the category MC, do you recover coalgebra cohomology?
Sorry?
What part? Should I start from the beginning, or?
So I have some problems.
Okay, so if you choose the algebra A,
yeah,
trivial, meaning the unit to be the unit object of your category MC, what does your cohomology give? Does it give coalgebra cohomology in the sense of Cartier?
I'm afraid that I don't understand your question.
Your construction has two ingredients, right? C and then A.
Yeah, but they live in different worlds. C is a coalgebra in the classical case, in the category of vector spaces,
exactly.
And A is an object in M.
In MC. M depends on C.
In AC, okay.
Right. So you can take the unit object of MC.
Okay.
What happens then? That's the question. Do you recover coalgebra cohomology or something familiar, or does it trivialize completely in that case?
A good question. We missed it.
I have a very elementary question. On the very first slide, even before you got into, when you still discussed Gerstnaber's situation.
Not this.
No, a little bit further. No, it's further. Oh no, here already. So here you say, not quite here, okay. So, but in any case, so you have a multiplication on an algebra,
yeah.
And then a formal deformation is an extension of this multiplication to the ring of formal power series. Yeah. A ring of formal power series in the variable t. If I understand you correctly now, this M prime that is here in the third line on the slide is the restriction to the constant terms of this multiplication.
Yeah, but things are more complicated because you don't use the usual tensor product on AT, tensor AT. You have to use the completion of it with respect to the periodic.
Yes, yes.
If you regard the M prime as a map from the completion to AT, then this M prime here is the restriction of the big M prime.
Yes. So my question is does the restriction to AT already determine the whole deformation? So the restriction to A.
You can go back. If you have such M prime, you can extend M prime to get an associative algebra in a monoidal category of some complete KT modules with respect to some tensor product.
Is this step where would this be written up, that if you can have an M prime like this, which is only the restriction, that you can really go to the whole completion? Where do I find this in the literature?
This is Gershon-Haber's stuff, I suppose.
Okay.
There is a proceedings of a NATO meeting on deformation theory, I don't know, 86.
Okay.
And there, Gerstenhaber included 200 something pages, long pages survey, and you can find details in that survey.
Okay.
Also, there are some information in Castell's book on quantum groups.
Okay.
At a certain point, he is interested in deformation of UG, enveloping algebras, of course.
Definition of the deformation? In fact, the definition of Gerstenhaber is to take m prime to be from AT, tensor AT into AT, but KT linear. Exactly. Yeah, this is the right definition. But if it's KT linear, then it reduces to take only m prime on A tensor A into AT because of KT linearity. Yeah.
Well, continuity is not a problem because you work with complete space, topological spaces, and it comes for dyadic is fulfilled automatically.
If you start from, so the m prime is determines it if the original one was continuous, and vice versa, right? This is the situation.
Okay, there are more questions? If not, let's thank the speaker again. And let's thank to all speakers of the conference.